This is one of the most important lectures in the OCT series, OCT imaging in non-transparent tissue. Most of the tissue in the body is non-transparent, the eye being an exception. It's not a surprise OCT can image in transparent tissue like it can image in an optical fiber, but non-transparent tissue, by definition, does not let light pass through easily. I have not been subtle over the fact I was not directly involved in imaging in transparent tissue of the eye, nor was I actually interested. I entered the field to develop it for non-transparent tissue. OCT in transparent tissue developed over 2 decades, and it started with imaging cracks in fiber optic cables. When I entered the field in the early 1990s, it's safe to say imaging in non-transparent tissue was universally unsuccessful. Here we're going to discuss why imaging is so difficult in non-transparent tissue, how we and other groups overcame these issues, and how penetration can be improved even further. This is very different than the ophthalmologic research. The ophthalmologic research, the tissue was transparent, so it was primarily improving engineering. But we're going to see that the studies in non-transparent tissue, because of particularly of the high scattering, which you can't generate theoretically, figure out what the results will be. This was very hypothesis driven, and it was driven by the physics more than it was driven by the engineering. So my name is Mark Brezinski. I'm sure you're sick of seeing my background. This, again, not a plug for my book. The material discussed, the material is discussed in far more detail in my book. Chapter 3, Light in Matter, and Chapter 7, Noise and System Performance. Eye tissue is designed to let eye in. It's transparent. Non-transparent tissue particularly scatters but also absorbs, making OCT imaging challenging. You can't, this is a critical point. An ophthalmologic system will not work in non-transparent tissue. So you can't image coronary arteries or GI tract with an ophthalmologic system. They're essentially, this is two different fields. And then we're going to get into the concept of noise, signal, and noise. We're going, the dynamic range of transparent tissue is very small, but in non-transparent tissue, the difference between the surface and the signal you get and deep within the tissue is let's say 100 decibels. And so you need system performance that can get that entire range. So again, if you used an ophthalmologic system in the eye, it wouldn't work. And so it would only penetrate less than 300 microns. This was the state of the field when I entered it. You can understand why there was so much skepticism and few people worked in it. And if imaging was not successful in non-transparent tissue, which was achieved roughly between 1993 and 96, then I don't know how much widespread interest in the technology there would be, or technological advances. For instance, the cardiology application drove a lot of technology advances that ultimately would be used in ophthalmology. And so, the non-transparent tissue work pushed the ophthalmology work, but in fairness, a lot from the ophthalmology work was used for non-transparent tissue. A critical point. we're not talking about light penetration, we're talking about imaging penetration. So light penetrates in non-transparent tissue easily millimeters, but that light is reflected all over the place and bounced. So and we need to measure single scattering events. Light goes in, bounces, comes back. All right. So um, at either at either 800 nanometers, which is what's used in ophthalmology, or 1300 nanometers, which is used in non-transparent tissue, light penetrates many millimeters. But from an earlier lecture, OCT is a ranging-based technique. Here, this means that a photon is sent at the sample and back reflected just once toward the detector. It can't bounce around or the time of flight will be inaccurate. I'm going to give you a classical description of that. Imagine you have 1 millimeter of tissue on a reflector like a mirror. If it goes in, comes back, that time of flight is calculated by the system. I'm going to use the word calculated, and then plotted as 1 millimeter. If the photon goes in, hits the mirror, bounces around 3 times, comes back, it's got a longer time of flight. So when you look at the image, you'll have pixels filled with backscattering that looks like the light is penetrating into the mirror. So it's a fake out. It's the time of flight is longer than the distance of a single scattering event. This is called multiple scattering, and it also reduces resolution. So you're losing those photons, and you're widening the point spread function or reducing resolution. And we'll come back to this numerous times because it's critical. So OCT does not measure the total light reflected back. You need to measure the single scattering events, and then non-transparent tissue sends back predominantly multiply scattered light, which we don't want. We want to filter that out. I'm going to illustrate this point with this slide. This is a drop of blood on a metal reflector. The reflector is horizontal, but it looks curved. So the top is the surface of the blood, blue arrow, and the green and red arrows are pointing to the reflector. So it looks horizontal, it's horizontal, but it looks curved because light travels slower in blood, or the blood has a high reflective index. This is a classical description. The blue arrow, again, is the surface. The green, if we look at the green arrow first, where there's little blood over the sample, you can see that the reflector is sharp, and you have minimal fake reflections from behind it. But when we look at the red arrow, now it's much more diffuse. We don't have a well-defined resolution of the reflector, the mirror. And then it looks like signal is coming from within the mirror itself. You could see that the red arrow points to well below the surface of the mirror. But this isn't possible. So this artifact is caused by multiple scattering, the time of flight. So what affects imaging penetration? Absorption to some degree in non-transparent tissue, but we've somewhat controlled for that. Scattering is a big one. And then you need to be able to detect really broad range of photon densities from 100 decibels to 1 decibel in terms of the signal to noise ratio, which is a very high signal to noise ratio. And we're going to come back to this in another lecture with the spectral domain techniques, which have a lower dynamic range, and therefore you don't optimize penetration. based on our work, you have better penetration with time domain OCT than with spectral domain OCT. Now, this paper wasn't done by our group, but it was critical in deciding the direction to develop OCT for imaging in non-transparent tissue. I don't think I would have even entered the field if I hadn't read this paper. Now, the top is absorption versus wavelength, and the bottom is scattering versus wavelength, and this is liver. So if this was the eye, that scattering curve would have a lot less scattering. It would be flatter. So the green arrow shows where you perform imaging in ophthalmology. And the hypothesis when I entered the field, examining this data in particular, was that the area where the red line is, that both scattering and absorption are low. You'll notice there's an absorption peak for water at 1500 nanometers, but we're down around 1450 or 1300. Sorry, I was off with my wavelengths a little bit there. I was thinking of something else. 1300 nanometers. And the green line is also the wavelength used in telecommunications. And we call this where the red line is, where you have low scattering and low absorption and optical window. As I pointed out in previous lectures, this was the papers that established OCT imaging in non-transparent tissue. What was involved is discussed particularly in the paper on the history of OCT, or the video on the history of OCT. So this illustrates this concept of the optical window. So if we look at the middle image first, if you image the epiglottis at 850 nanometers, and this comes out of that circulation paper, you don't see the cartilage below. You're just getting the surface, and the surface details are poor. If we look at 1300 nanometers, penetration is down. Not only do we see the cartilage, we're imaging the back of the cartilage, and it corresponds to the histology on the bottom. Now, in terms of discussing scattering, I want to start off with an example of red blood cells to get into the principles of scattering. I want to say scattering theory, but with the caveat that there is no great scattering theory particularly for biological tissue. It's too complicated. A lot of it is empiric, but the theory can be useful in leading you in certain directions. And there's a lot of examples of this in medicine too. So the images here are from the first in vivo intravascular imaging study. It was done by our group. The study is discussed in more detail in the history of OCT video and in the paper. The top image is the aorta in the presence of a saline flush. And you can see the walls well. You actually can see into the adventitia and structure within the adventitia. But saline is optically transparent. The bottom image is done with just blood, where only a small portion of the wall is seen. Up to this point, it was felt that blood scattered because of the large numbers, but the scattering was coming from the membranes, the organelles like mitochondria and endoplasmic reticulum. And this just didn't make sense to us. These structures were too small relative to the wavelength to be scattering, and we're going to go into that in more detail. And so we had a postulate, but we tested it. So in this slide, the top line in each one of the images is the surface of the fluid, and the bottom line, if you see it, is the reflector. So first there's saline on a reflector, and saline is optically transparent. The second image, there's blood, which does not allow any imaging penetration. And then we lysed the red blood cells and resuspended them. So all the material's still there. There's cell membranes, there's mitochondria, there's organelle, and we got back over 75% of the signal, and similar results with plasma, and similar result to plasma. So it clearly was not the cell membranes or the organelles. So what does cause reflection? And we're going to go into, it's actually several things that are key in reflecting the signal back, but there's one critical component, and again, this is the same image in the top of the last figure. So the top is the saline surface and the bottom is the image. And so um, and this is a droplet, that's why the surface is a little bit curved. And so uh, the above the water is air, and then the second reflection is a metal reflection. So why does a reflection occur? This is a basic principle. You don't get reflection if there is not a difference in the refractive index. And we discussed the concept of a refractive index in one of the previous OCT physics lectures. So the refractive index of air is 1, saline 1.35 roughly, and the reflector is greater than 1.5. If you have two glass slides with an air gap in between, you see the surfaces between the slides with OCT. But now if you take those, that's because the air and the glass have a different refractive index. If you take those same glass slides and press them together, you do not see any reflections from the surfaces that are in contact, because it's glass on glass refractive index with equal refractive index, so it will be transparent. So when we look at the red blood cell, we have a refractive index inside the cell and a refractive index outside the cell. And it has nothing to do with cell membranes or organelles. And so now, how do we image through blood? We can deduce this to some degree from the last image, but scattering theory. And I want to caution that, in my opinion, scattering theory is only of very limited value in highly scattering tissue. But this type of analysis does give us sort of a guideline. Tissue is just complex and variable. And it's funny because I think I mentioned this in a previous talk. In the early days when we first started showing OCT images of various non-transparent tissue, I did a presentation at a Gordon conference. I think it was at Dartmouth, and then the next speaker came up with scattering theory and said that OCT would never penetrate more than 300 microns. And so somewhat of a disconnect there. But this paper is by a prominent optics pioneer, Burton Chance, at the university, from the University of Pennsylvania. It shows a Mies scattering or Mies approximation. When we look at the symbol on the left to the equal sign, we're just going to take that to mean for here the total scattering. And the exactness of the equation doesn't really matter. What matters is the factors that are in the equation. So if we look to the right where it says index match, N stands for refractive index. So if the refractive index is different between N inside the cell and EX outside the cell, then that area in the parentheses is non-zero and the equation has scattering. If those two terms are equal, then with the -1 sign, scattering goes to 0. So that illustrates this critical point that if you can equalize the refractive index inside and outside the red blood cell, blood would be transparent. I just want to point out that there are other parameters in this equation which are relevant. The wavelength you use absolutely determines scattering and what will scatter. And then the relative phase. So if you have something like a clump of lipid, you're actually getting re-radiating from the molecules of lipid, and when they come out, their phases add up. There's a phase factor in here. So size of the scatterer plays an important role in shape along with the mismatch. So we introduced the concept of index matching, which apparently its name is changed to optical clearing. And this is again in the circulation paper. And this is hypothesis-driven empiric work, but with using scattering theory as a baseline. And so I'll show you the experimental setup on the next slide, but the goal is to raise the refractive index of the serum. So what we did is we created a in vitro system. We put a reflector inside tubing, pumped it, we had a reservoir, and we could add material to the reservoir. So, and changed the refractive index of the serum. So in this experiment, we went with things that would not go through the cell membrane to any significant degree. So here we used a contrast medium, an X-ray contrast medium. So on the left is just an image of through blood to the reflector, and you can barely see the reflector. On the right, this material, which we don't have to go into detail in, but it has a high refractive index. I think it was like 1.7, but it raised the serum refractive index, and we recovered most of the reflection. And so Dextran was great. At some points it got up to 100% of the penetration back, or close to 100%. Contrast medium was around 50%. When it says saline here, this is not compared to pumping saline through the tubing. It's the saline vehicle that we used with the Dextran to show that it wasn't being caused by the vehicle. So it was blood with a small injection of saline in it. Sorry for the font on the slide. I don't know what happened, but this is a useful beginning to scattering and how you can overcome scattering problems. We're not going to go into an extensive amount of detail into scattering. This is the subject of books, but the yeah, don't even remember what I was going to say. So what happens when light enters medium? And this is where it gets confusing to people because, okay, well, what happens when you send the light beam through water? Are the water molecules scattering? And how is it different if you have a water droplet in lipid? And so what happens is, this is from my textbook, but it was modified from the great Hex textbook of optics, which is a great optics resource, and I highly recommend it. When light hits a molecule like water or lipid, the molecule oscillates. If it's near the resonance frequency, and like a guitar string has a resonance frequency, then it'll be absorbed. If not, the radiation oscillates the electron. And so if we go back to Maxwell's equations, which some of you may not know Maxwell's equations, it's discussed in the textbook, but a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, and that was discussed also in the earlier physics uh, lectures. But so you re-radiate energy, but you don't necessarily re-radiate it in the same direction. And so you have to add up um, the phases and intensities of all the molecules that are being re-radiated. And again, this is discussed in far more detail in the textbook. So now, if we have a few scatterers like this that are irregularly arranged, then what's going to happen is their phases are going to add up in a complicated manner. So if we take calcium in water, how does it scatter? Well, it depends on how the molecules are arranged. Calcium chloride actually has some degree of penetration, but if aggregates of calcium in lipid, because of the high mismatch, really the penetration is extremely poor, and you get shattering. So let's look at some of the other approaches for dealing with scattering in non-transparent tissue. So among the other approaches are parallel ultrasound, and this is something we introduced, and I'll show you on the next slide, and it hasn't really been taken advantage of. Image processing and controlling the signal to noise ratio. And these are just some examples of how to improve the situation. So I'm not going to go into that much detail about this, but our first paper on this was published in the Proceedings of the National Academy of Sciences. And then we looked at intensities of ultrasound and frequencies of ultrasound in the second paper in the Journal of the Optical Society of America. But so what happens is that an OCT system as a whole will filter some multiply scattered light. It's got what's called for instance, a bandpass filter in it. So it blocks out frequencies or distorted light that's coming back. That's somewhat of a simplification. But now imagine if we have light going straight in and straight out, and we send an ultrasound beam parallel to it, the ultrasound beam will not shift the frequency of the light. And I'm going to explain why that's important in a minute. Because if you shift the frequency too much, it's filtered out. But if the light scatters around, multiply scatters, it has a lateral component, not just into the tissue, but it's going sideways. And this is a very classical view, and as somebody who does quantum mechanics, it's sort of disturbing explaining things this way, but we'll just use this as for illustrative purposes. So now that ultrasound beam, it's called a photon-phonon interaction, but the ultrasound frequency is picked up by the photon of multiply scattered light, but not single scattered light. It frequency shifts it, so when it returns back, it's outside the filter, bandpass filter, the filter that allows only certain ranges of light to be detected, and you've just removed multiply scattered light. Sorry, this slide showed up twice and I don't really know how. So that was one example. And then image processing is another way of uh, improving imaging penetration. Um, Based on the last slide, you could tell that don't have a lot of time to put these presentations together. I do the best I can, but there's just a lot of topics to be covered with OCT. So in our group, fortunately, my colleague Ika Rogowska, right from the beginning, has done incredible work. So um, there's only 3 chapters in the OCT book that I didn't write, but image processing was one of them, and uh, that's because Dr. Rogowska knows so much more about this area than I do. And so I'm just going to show you, with regard to what's covered in the textbook, these are the various techniques you can use to improve imaging. And I'm just going to explain one of them. So um, we published this, you could see it down below. We published something called the sticks technique um, in earlier work, and it's shown below the references. And it was based on another group's work, nonlinear image processing by a rotating kernel transformation, which I'll explain in a minute. But I think that if you're interested in understanding it, I thought that this cartilage, we did automated edge detection of the bone cartilage interface in this paper, and it's a much more simplified description of the approach. So now it's a pretty clever technique, and I can say that because we didn't come up with the initial concept, we just refined it. And so what you do is that um, if you're just looking at one pixel, there's chance that you're going to end up with a lot of error, scattering, noise, a variety of things. So what you do is you create a stick. So if we look in the upper left-hand corner, we have a stick of 7. And so we take that and then we use for the center pixel the average of all those pixels. Then it's rotated. And you can do this. This occurs very quickly with the computer. And now we have another average for that center pixel, and you rotate it all around. And then the net value is what you assign that pixel in the image. And this removes a lot of the noise. But in this particular case, what we were trying to do is isolate out the edge between cartilage and bone. So on the right side of the image is a picture of cartilage on bone. And so if you look at the bottom, what that did was it defined the layer. So there wasn't, it's very smooth and it's very easy to pick up. Automated, the computer picks it up and draws out the edge. And so, yeah, the bottom image was done with a K of 31. But again, with a very fast computer, modern day computers, this is relatively easy to do. So this just gives you an example of one of the many image processing techniques. We like this. We like this for elastography. We like this for automated edge detection, for improving resolutions in certain cases. And we'll come back to extracting signal from low noise. And I just wanted to point out that image process, this is a 2020 paper doing corrections for aberrancies. This is, again, the bulk of most OCT papers right now is in ophthalmology, transparent tissue. But image processing work continues on and advances are made. And so they play an important role in OCT. Unfortunately, Uh, it's not. Um, a lot of the advances we have aren't really applied at this point in time to clinical imaging. So absorption. In non-transparent tissue, absorption plays less of a role at 1300 nanometers. The largest absorption is water, which peaks around 1500 nanometers, um, which is the resonance frequency. And again, we saw this in the paper. So if you look at around 1470, 1500 on the top curve, there's a water absorption peak. And I'm hopefully this isn't too distracting, but if we were to shift over the red line to 1700 nanometers, scattering is very low, but we're picking up more absorption than we have at 1300 nanometers, which makes that non-ideal. It's also very difficult to get optics and sources in that 1700 nanometer range, though it's a second option. Um, Now, an important point is that absorption is dependent on the distance traveled through. So in non-transparent tissue, we're going distances of a biopsy, roughly 3 millimeters. And so absorption isn't that critical. However, the vitreous humor of the retina, or of the eye, that's about 20 millimeters. So you cannot take the 1300 nanometer source used in non-transparent tissue and use it in the eye. You'll be absorbing the signal, but you're heating up the eye. Uh, I've been said, depending on the power, you could blow up the eye. I don't, I never calculated that out myself, but again, different areas. You can't use an ophthalmologic system in non-transparent tissue, and you can't use a non-transparent system in ophthalmologic in the eye. Um, there's also a technical reason. So we're imaging over 3 millimeters, and a little bit of absorption actually reduces the amount of multiple scattering. So a small amount of absorption may actually be beneficial. But anyway, let me just demonstrate the point that absorption affects imaging. So here's imaging of cartilage at 1300 nanometers and at 1470, the peak. And you could see the penetration is less. So how do we know this isn't from differences in scattering? I'm going to show you that on the next paper. I honestly don't know if this is published or unpublished data. Um, I published 150 papers. I remember doing this experiment, and I don't know if it showed up in a paper or not. So what we did is we took water and we put scatterers in water, and then on the left we imaged it in water, and you could see the reduced penetration in at 1470 nanometers wavelength. Now on the right, what we used is 3-to-1 ratio of heavy water. So the hydrogens were replaced by deuterium, and they don't absorb at 1500 nanometers. And so imaging was almost completely restored. Wasn't totally, because it's still 25% normal water. So the decreased penetration was due to absorption, not scattering. Dispersion is an important topic. It's an important topic when you use, particularly when you use very broad bandwidths to gain high resolution or over long distances, but it was covered in a previous lecture. System performance and penetration in non-transparent tissue. So this is critical to success And I published a paper um, in 2018 on the quantum theory of OCT because we want to try to get below the quantum noise limit. And a lot of what we learn is from other fields, and the people who've done this extremely well are the people who work in the discovery of gravitational waves. You've probably seen that on the news, the detection of gravitational waves. These people have done incredible jobs in reducing noise below the quantum noise limit. And it's not violating quantum mechanics, but I'm not going to go into the theory of how that works either here. So you can read about um, signal to noise ratio and SNR on the slide, or dynamic range. I'm not going to go into that in detail. But the signal to noise ratio um, is describes the light properties, the lowest signal to the highest signal. The dynamic range is what the device is capable of doing. The dynamic range is what's picked up by the computer. And this is it when it's digitized. You cannot digitize if you have a signal to noise ratio of 115 decibels. You're going to get a maximum of about 80 decibels in digitization, and that's explained in the book. But the but again, we need high signal to noise ratios and dynamic ranges, and I want people to be very careful when you see dynamic range close quoted, particularly for swept source OCT or spectral techniques, that the electronics formula is double times two higher, the way you calculate it, than the optical signal. So somebody could say that they have a dynamic range of 80, which has been what you quote for the opticals, but when you do it for the electronics, or sorry, that's the electronics. Uh, the optical signal may only be 40, but using the electron calculations, it's quoted as 80. So saying swept source OCT has a dynamic range of 80 is using the dynamic range of the electronics, not the optical field. That was pretty confusing. The point is, this was dealt with in a previous lecture on improving dynamic range and swept source OCT, and we will talk about it in detail when we compare time domain and spectral domain OCT. But time domain OCT has a better dynamic range than swept source OCT. But so in moving forward, think about that. But so this is from Stephen Beaupart's doctoral thesis. I'm not sure if it was ever published other than in this thesis, which is a published work. Stephen Beaupart was obviously a very talented student and now a very talented professor. But as you reduce dynamic range, you reduce both, or signal to noise ratio, you reduce both penetration and clarity of surface imaging. And I'm not going to go into detail on this. Again, it's discussed in the book, but we need that maximum dynamic range. And you get a less dynamic range with the spectral domain techniques than the time domain techniques. So OCT imaging in transparent tissue and non-transparent tissue are two different fields. And it was a critical breakthrough to get OCT to work in non-transparent tissue. and we still continue to advance it. And I showed some examples of how it was done. And who was involved in this is slightly different on this slide, the data that was presented, than in other slides. And this is not all the people, but again, a lot of the work was done. James Fujimoto and I did in collaboration. Um, it was done a little bit later. And two people not mentioned on the slide. Some of the early work was obviously done by Gary Turney, Brett Boma, and Stephen Bopart, who aren't on this slide, but other people like Wolfgang Drexler, Kostas Petras, Xingdi Li, um, Ika Rogowska has a PhD, and it's not listed on the slide, and Bin Liu, and here's some of our clinical collaborators and our outstanding technicians. Thank you very much.